Alright, great! It is time to outline our model. Consider pausing the video here if you feel like you need to revisit the introduction of TensorFlow we showed a few lessons ago. In this way, it'll be easier for you to see the parallels between the two exercises, and you'll know what to expect. Moreover, I'll go through the familiar parts of the code faster, without wasting time on things we already know. Okay, I'll start outlining the model. Let's start by drawing a picture that follows the logic. As we explained in the previous videos, there are 784 inputs, so that's our input layer. We have 10 output nodes as we one-hot encoded the 10 possible digits. We will work with 2 hidden layers consisting of 50 nodes each. As you may recall, the width and depth of the nets are hyperparameters. I don't know the optimal width and depth for this problem. I surely know that what I've chosen right now is suboptimal. It will be your homework to fine-tune the hyperparameters of our model and obtain improved results from the ones we have in this video. Alright, let's declare 3 variables for the sizes of the shapes. The input size is 784, the output size is 10, and the hidden layer size is 50. The underlying assumption is that all hidden layers are of the same size. That's a simplification quite often adopted in practice. Alternatively, you can create hidden layers with different width, depending on the problem you are trying to solve. Okay, the next line of code is tf.resetDefaultGraph. Essentially, we need this line of code to reset any variables left in memory from previous runs. This is an important thing to do, as the first time we build an algorithm, it is never the best one. Usually, we must play around with hyperparameters to find the ones yielding the optimal result. Therefore, each time we change them, we want to train the model from scratch. This line of code literally means reset the computational graph. The default word here refers to the fact that TensorFlow allows us to define several computational graphs and run them independently as different parts of the training. Throughout our examples, we're not making use of this feature, as we declare our variables globally, as part of the default graph that is. Right. Next, we want to declare the placeholders. The lines of code are the same as before, so I won't spend much time on this. Let's get back to our picture. We have the inputs placeholders. To lay down the model, we must define the other 3 layers. They are reached through 3 pairs of weights and biases, 1 for each layer and the activation functions. Let's get on that. This time, we will declare the weights using a different method. tf.get_variable. That's the conventional method to declare variables. It has several advantages, one of them being the default method of initialization related to the method is Xavier. There are 2 required arguments, a name for the variable and its shape. Nothing complicated. I'll call them in the same way as I name the variables. What about size though? The weights have the shape, inputs by outputs for the respective layer. So, for the first weights, we have weights1 equals tf get variable of quotation marks weights1, comma, input size by hidden layer size, and biases1 equals tf get variable of biases1 hidden layer size. The size of the biases equals the number of nodes in the following layer. Simple as that. Alright, let's find the nodes of the first hidden layer. I'll call them outputs 1, so we'll have names consistent with the weights and biases. Time to apply an activation function. I'll go for ReLU, as I know it works well for this problem. But does it really matter? Well, you'll find that out on your own for homework. Let me write this line of code. You'll get it right away. Outputs 1 equals tf nn ReLU of tf matmul inputs weights 1 plus biases 1. Basically, we are applying a ReLU activation to the linear combination of the inputs and weights plus the biases. Nothing new theory-wise. In terms of code, tfnn is a module containing, among other things, the most commonly used activation functions. The activations we have seen are tfnn sigmoid, ton, ReLU, and softmax. Remember that, as you'll need it for the exercises after we are done. Alright, so we have our first hidden layer. Completed analogically, we stack the second one. Weights2 equals TF, get variable of. Weights2, hidden layer size, hidden layer size. We can confirm the shape of the weights from our picture. Biases2 equals TF, get variables of. Biases2, hidden layer size. This time, we refer to the number of hidden nodes in the second layer. Finally, outputs2 equals TF, NN, ReLU of, TF, matmul, outputs1, weights2, plus biases2. Obviously, I chose ReLU again. The multiplication this time is between the hidden nodes from the first hidden layer and weights2, while the appropriate biases are biases2. Easy. That's how we stack layers. We declare the respective weights and biases, and then we calculate the following outputs. After seeing it once, you can do it on your own. In fact, you will do it on your own if you practice what you've learned. The final weights and biases are declared in the well-known way. The size of weights3 is the hidden layer size by the output size, while the size of the biases is the output size. This time, we will call the outputs outputs, and we will only calculate their linear combination. Obviously, you can use the same syntax as before and apply an activation function. But I want to show you a little trick we haven't discussed. It is common practice to incorporate the activation of the output layer in the loss. We will see how that's done in our next lecture. Thanks for watching.